So let's examine how certain solvents stabilize Sn2 reactions, thereby increasing the rate of those reactions. Let's begin with the following statement. Polar solvents usually stabilize molecules that have charged atoms. So let's look at the following reaction. Let's suppose we have two neutral reactants. We have a nucleophile and our substrate containing our leaving group. These two reactants react. This pair of electrons attacks the carbon. A bond between N and carbon begins to form. A bond between carbon and L begins to break as this leaving group begins to leave. And our transition state for this reaction looks as follows. As a bond between N and C is beginning to form, a bond between carbon and L is beginning to break. That means that on this bond, electrons will be closer to the L, and so this will have a partial negative charge. Likewise, the electrons approach the carbon, and so this N will develop a partial positive charge. So our transition state will have partial charges. Our reactants will be neutral. Now let's examine our products. So when our products are formed, this bond has completely broken, this bond has completely formed, so now we have a full positive charge on the end and a full negative charge on this leaving group. So neutral species, partial charges, and full charges. So let's suppose we take some beaker, some container, and we place a non-polar solvent, let's say some hydrocarbon, inside our beaker 1. And let's say we place these two reactants into that beaker and a reaction takes place. Now let's draw the energy versus reaction progress diagram. Let's suppose that our energy of reactants is higher than energy of products. So let's say our reactants are somewhere here and our products are somewhere here. Now this black line represents our non-polar solvent reaction. It represents the beaker with the non-polar solvent. So with the non-polar solvent, our neutral reactants are found here, our transition state is found here, and our full product, or our products with the full charges, are found here. So, in order for this reaction to take place, this amount of energy needs to exist because this is known as our activation energy, activation barrier. And this energy is the energy of our transition state. Now, if we use a non-polar solvent, the solvent will not stabilize the charged molecules because the solvent molecules don't have a net polar moment. Remember, non-polar molecules themselves have individual polar bonds, but overall the net charge is 0. And so there is no partial negative or partial positive charge to stabilize these charges here. On the other hand, a polar solvent contains polar bonds and therefore will stabilize charged molecules. So for example, let's take this transition state. So let's take a second beaker, let's place water, a polar molecule solvent, inside beaker 2, and now let's place our neutral reactants. So these guys will react, they'll form our transition state, and then become the products. So let's examine our transition state. So this is the same molecule as depicted here. We have a partial positive on the N, partial negative on the L, and the bond between NC is being formed, the bond between Cl is being broken. If we have water molecules around our transition state, the electronegative oxygen will have a partial negative charge, and that means it will stabilize this partial positive charge. Likewise, from this side, the same thing happens. On the L, we have a partial negative. That means the partial positive charges on this H atom, on all these H atoms, will stabilize this negative charge. They will cancel out, thereby stabilizing it. So this will be stabilized. Now let's look at this situation. Now we don't have a partial positive negative, so we're going to have a full positive charge on the N and a full negative charge on the negative. the larger our charges, the more stabilizing our polar solvent is, because the more bonds we can form. Notice how we have more oxygens now around this larger charge than before. And we have more H's around this leaving group. So now these guys are stabilized even more than transition state because they have a larger charge. This has a full positive charge and a full negative charge. Now this will also be stabilized, by the way, but less than this or this, because these are relatively neutral compared to these guys. So let's examine our polar solvent. So this black reaction is with the non-polar solvent. This reaction is with the polar solvent. So purple is polar, black is non-polar. So these will be slightly stabilized. So that means it will drop only slightly in energy. So we begin with this much energy with the nonpolar, and it's stabilized slightly, so lower in energy than before. But at transition state will be stabilized even more than before, because this has a partial positive and partial negative. So this will drop in more, or this will change more than this guy. So the change here is larger. And that means our activation energy is now smaller. So if activation energy is smaller, what happens to our rate of reaction? Well, it increases. And then notice our products will be stabilized even more than reactants or the transition state. And that's because this is a full positive and full negative charge. So once again, in this reaction, the transition state will be stabilized by a polar solvent more than the reactants, because the reactants are neutral, and less than the products, because the products have full charges. Since activation energy decreases and activation energy determines the rate of reaction, the forward reaction will increase. This rate will increase because transition state is stabilized than our reactants. Now our situation could be completely opposite. Suppose the reactants have full charges, while this transition state has partial charges. That means if this has full charges, this will be stabilized more than this guy, and then our activation energy will increase. And so sometimes our polar solvent or our solvent will act to increase the rate of Sn2 reactions, while other times our solvent will act to decrease the rate of Sn2 reactions.